Hello again, my dear students, and let's continue our investigation with the CMOS-based temperature sensor. If you remember, my dear students, in the previous part, we have reached an equation under the name of reference voltage or V reference. So the equation said V reference equals K over Q alpha ln PR T plus VP. As a question would, what does the word reference mean? A reference voltage is a voltage that should show independent performance with respect to the input. That's why we call it a reference. So, as we are here investigating a temperature sensor, this V reference should show independent on temperature. In other words, we can say that partial V reference by partial T should be equals to 0. So how we can do so, or is this applicable? Can we manage to have the variation of the V reference with respect to temperature equal to 0? Let's see. So by differentiating this equation simply, as you can see, K over Q ln PR alpha is the constant. So here the differentiation would be straightforward. K over Q alpha ln PR. And another term, which is partial VPE by partial V. As you know, we already investigated this in the first part, that this is uncontrollable term because VBE, generally, if you remember, VBE equals KT over Q ln I2 over IS2, if you remember that. So, generally speaking, this VPE is a complicated function in temperature. It's a function in directly in temperature. It's function in the current and the saturation current, which are indirect function of temperature and so on. So from one side, we can say that this variation, which is partial VPE with respect to T, is uncontrollable parameter, but definitely it is a measured parameter. You can measure it in lab. Simply, you can put the circuit and change the temperature and change the VPE and so on. Okay, so let's assume that we go to the lab and we did let's assume that we go to the lab and we did an experiment to investigate this variation. So here we have the temperature axis, and here we have the VPE axis. And after doing this experiment, we get some sort of a curve like that. So while changing the temperature, the VPE drops by this linear behavior. Again, the question is still open. Is it possible to have a V reference which is a temperature independent? Surely VPE is a temperature dependent. But how we can manage this? Let's now focus on this alpha parameter. If you remember, we just insert alpha as a multiplication to the delta VPE without any critical need for that. But using this equation, and in order to apply or to tend this equation to 0, you can say that, okay, alpha, or let's let K over Q alpha ln BR plus partial VPE by partial T can be equal to 0 if we manage to have alpha equals to minus partial VPE over partial T times Q over K ln PR. So you are now intending to have alpha, which is still a temperature dependent. Instead of having alpha a constant, it will turn now to be a temperature dependent parameter. But its temperature dependent is typically the reverse with respect to the VBE dependent. So if you have a VBE dependent with respect to temperature in this manner, then you will have a reverse manner, looks like that. The summation of these two functions, so this is the VPE, and this is alpha times delta VPE. The summation of these two functions will end up with a constant, and this is what we call the reference. So the process of the reference voltage is simply the process of adding two elements. Each of them is temperature dependent, but in a reverse manner, so that the summation of these two terms ends with a constant. Let's see this on graph. So as you can see here, my dear students, you have two temperature dependent functions. We have the VPE, which gives this negative slope with respect to temperature. And you created this alpha delta VPE to have a negative response so that the overall voltage is kept constant. This is one of the very essential voltages in electronics, what we call the band gap voltage. And as you can see, its definition that it's a voltage that is temperature independent due to the summation of two temperature dependent components. Okay, that's great. Now we pick up the process. Now, if you return back to the schematic, my dear students, you will find we have two terminals. We have a terminal, which is VB-TAT. If you remember, this is simply alpha delta VPE, and this represents the variation in temperature. So whenever the temperature change, this delta VPE will change, and then the VB-TAT will change automatically or accordingly. And we have the reference, which is a constant voltage, reference voltage with respect to temperature. Now, we can turn those into numbers. So, for example, if we go to this example here, you will find that this is alpha delta VPE, which express a variation in the temperature between negative 273 or 273 Celsius up to 33 Celsius. And this can be a function, so you can easily express this function in terms of what we can call the mu. The mu is simply a normalization factor between the VP-TAT, which is a reflection on the change on temperature, and V reference, which is constant everywhere. So it seems like you have a normalized version of your voltage. So if you just express it in a very simple manner, VP-TAT is simply alpha delta VPE, and V reference is VPE plus alpha delta VPE. So you know that the main variable here is delta VPE. Delta VPE is varying with temperature. Let's consider first the extreme conditions. The extreme conditions happen when, for example, delta VPE is equal to 0. I mean, the voltage is, or the temperature, the temperature difference is very, very, very big, so that the delta VPE will tend to 0. If the delta VPE tends to 0, that simply mean that, or I'm sorry, the temperature difference is very, very, very small. So very, very, very small, so that the delta VPE is equal to 0. So in this case, you will get mu equals to 0. So this is the minimum value of mu to have it 0, which is somehow a theoretical conditioning. On the other hand, whenever the temperature increase or the temperature difference increase, whenever the variation starts to increase, so that when we reach, again, let's start here. Here, this appears with 0 Kelvin when you have, because simply delta VPE in the equation, you remember, it's K over Q ln PR times T, and T in Kelvin. So when you have T equals to 0 degree Kelvin, then you will have this negative 273 variation. Then you are going to increase a little bit higher and higher to reach the normal operation region. Then with increasing the mu, with increasing the temperature, the delta VPE increase, and so on. Ideally speaking, the maximum value of mu is 2 tends to 1. So if this delta VPE is very, very, very large, then you can ignore VBE with respect to delta VPE, and then mu will tends to 1. So the theoretical extreme value with mu is 1. So generally speaking, you can say that mu vary from 0 to 1 based on the value of the temperature. But as you can see, my dear students, that practically speaking, this is a very wide range with respect to practical measurements. For example, usually when you are going to make a temperature sensor, it's very rare to reach a negative 273 Kelvin Celsius, or it's very, very rare to reach 300 or 350 Kelvin, Celsius, except if you are putting this in furnace, or for example, or something like that. Usually the normal, let's say, for example, if we are going to put this temperature sensor in a water boiling tank, for example, then let's say that the normal temperatures, or let's say, example that we are putting this to measure the temperature in a room or whatever, the normal temperature is varying from, let's say, here they give an example, from negative 55 to 120. So as you can see, that the main drawback of this design is your scale of interest, which is from negative 55 to 125, is very, very narrow. It only represents 30% of the huge scale. So here we say that your limit of sensing is much wider than your needs. And this results with that you are not utilizing the full scale. You will not reach a mu 0 condition, or you are not going to reach a mu 1 condition. So what you are going to, or what one of the proposals in this direction is to efficiently utilize your scale. One of these solutions is simply, as you can see from this graph, is to change the slope. As you can see here, when we double the slope, which is this case here, as you can see here, we double the slope. We double the slope of the denominator and we fix the denominator. So V reference is still the V reference, it's the same. It's impossible, or it's not allowed to touch V reference, because this V reference should keep a constant parameter. But what you did simply is that you double the VP tat. You amplify the VP tat by a factor of 2. Here, that will be the results. So you now utilize the span, or the dynamic range of mu, from nearly 0 to 1 within your interest, your temperature range of interest. So here you can adjust your scale of interest with respect to your temperature range by simply adjusting this factor 2. You can make this 2 to be 1.5, could be 1.3, it can be 0.9, it depends on to what extent you are compressing or stretching your scale. The main important point here, my dear students, is that the scale of measurement can be still tunable during this process. So to sum up, we found that we have 3 main designing parameters in this schematic. The first is the P, which is a very critical parameter toward first compensating any mismatching effect between the two transistors. Second, to adjust your sensitivity, which is the minimum variation occurred in the output due to a minimum change in the input. A second design parameter is alpha, which is a key parameter in reaching a re-reference to be a temperature independent process by making a reverse dependent between the two components, resulting with a reference voltage which is temperature independent. A third important parameter occurs with an extra amplification or maybe attenuation for your VB-TAT. So this simply happens when or by inserting another amplifier here. For example, in this case, they double the value of VB-TAT before reaching the digital to analog converter, or maybe, as I mentioned, you can change the value based on your needs to adjust what we call the limit of measurements. So you can now adjust your limit of measurements by these two factors, which is, of course, a tunable factor. Herein, we have to recognize a very important point, my dear students, which is adding one more stage amplification stage here. It's not a zero cost process. Please don't forget this schematic. This is simply a schematic for an operational amplifier. So this operational amplifier inserted here to act as a differential amplifier with an alpha gain is not actually a simple triangle. It's a huge, complicated schematic of transistors connected together to perform as an operational amplifier task. Another one will be added here to amplify, for example, the VB-TAT. Again, you are adding more and more schematic or transistor to your circuit. This results in more complicated design and more power consumption. So this trade-off should be considered whenever you are doing your design. Thank you very much for your concentration, and let's meet in the next chapter, in the next schematic, with biosensing using organic field effect transistor. Thank you very much.